Okay, today, differential equations. And we're actually going to start with the derivatives. We're starting with differential equations. An equation involving a derivative is called a differential equation. Oh, imagine that. Involving a derivative is a differential equation. The order of the differential equation is the highest degree involved in the equation. One method of solving differential equations is to use antiderivatives / integrals, which is what we are going to start today. We're going to start with the derivative and come up with the original equation. I have down here differential equations, also referred to as ODEs, ordinary differential equations. The only math class in college that I'm sorry I did not take was ODEs. I actually didn't have to take ordinary differential equations. It follows the calculus sequence. You can actually do it after calculus. I didn't need to. If I was doing the applied calculus route, I would have done that. I was doing a teacher preparation, which is a more of a theoretical mathematics degree. I had to do number theory and a few other things which are more theoretical than applied. I didn't have to do ODEs. I was a returning student. I already had a son and was married and had a son at the time, so I wanted to get through school as fast as possible, get my degree so I could get to work. If I had the extra time, if I had really thought about what I was doing, I would have taken ODEs. They're extremely useful. You basically have an equation that is describing the change, and you want to go back and find, what's going on with the position and things along those lines. You're basically working backwards, and you can't find the equation you cannot deduce from the information the equation that describes the original situation. You can only describe what's changing due to your observations or whatever, which is why a lot of science classes use it, because it's easier to observe state change than it is to observe what's going on, and to describe that change rather than describe what's happening at the moment. And if you can come up with an equation that fits that change, you can go backwards. That's what ODEs do. That's what differential equations do. So we're going to work on solving them. Example number 1, find the general solution to the differential equation. So your differential equations are generally written as dy dx equals some function. The ones we are doing are all relatively simple, and they all involve the same steps for solving. Your first step, dy's and y's on one side, dx's and x's on the other side. Seeing as how I don't have any y's, all I have are the dy's. So I have dy on one side, I want all my x's and dx's on the other side. So I multiply both sides by dx. Now, technically, there are some people that say you can't do that because technically dx is 0 and you can't multiply. That's correct. But basically, this is how you solve the problem. So you get dy equals the secant squared x plus 2x minus 5 dx. And technically, there are parentheses around everything, but you don't have to really worry about that here. Okay? Now, I want to get rid of the derivative, which means I integrate both sides. And how do I solve the integral? I take the antiderivative of both sides. The antiderivative of dy is y. Because how many dy's do I have? I have one dy, right? And what's the antiderivative of 1? The antiderivative of 1 is whatever variable you have. In this case, it's y, so it's 1y. I don't have 1 written in front of the dy, right? Because we don't write 1, because if I have dy by itself, how many do I have? I have 1 of them, so I have a 1 there. Just like, you don't write 1x, you just write x. Why? Because we're lazy. Mathematicians are lazy. We don't write crap we don't need to write. We don't put 1x because how many x's do you have? You got 1 of them. Putting the 1 in front is redundant. I do, we are a lazy lot. We love to do our work, but we hate to write it. Okay. Equals. Take the antiderivatives. Okay, the antiderivative of secant squared, tangent x. The antiderivative of 2x, x squared. The antiderivative of -5, -5x. And then I have to have plus c. You absolutely need to have the plus c. You have to have that constant of integration. That's what that's referred to as. The constant of integration. You have to put the plus c in there. Okay? We didn't do it when we were doing the fundamental theorem of calculus. That's because we had bounds, and it was any solution. So we're using plus 0. Okay, which we were okay with. That's it. That's your first step. That's how you do it. How do you solve a differential equation? That's how you solve a differential equation. Don't worry, it doesn't get more difficult. Okay, but that's it. This is the first method of solving a differential equation. Separate the variables, dy's, dx's, integrate both sides, solve the integral by doing an antiderivative, plus c. As long as the functions aren't hard, piece of cake, right? Your turn, do that one. Okay. First step, dy on one side, dx is on the other. So I have dy equals the sine of x plus 4 minus 3 over x dx. And then to solve this, I take the integral of both sides. So I get y equals, the antiderivative of the sine of x is the negative cosine of x. Antiderivative of 4 is 4x. The antiderivative of negative 3 over x is 3 ln of x. 3 minus 3 natural log of x. Because it's x to the first power in the denominator. The antiderivative of the 1 over x is the natural log of x. And then plus c. Okay. Questions?
What happens to the dx?
Well, when you did the antiderivative, what happens? It goes away, right? When you integrate the derivative, because remember, the integrals and derivatives are inverse functions. Okay. Example number 2. Find the particular solution. And we've done this. You did this with other parts. Find the particular solution. In other words, find the original equation, y equals blah, 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 that passes through that particular point. One that goes to the point 0, 5. Process is the same to begin with. First step, dy is on one side, x is on the other. dy equals e to the x minus 2 dx. Integrate both sides. Y equals, the antiderivative of e to the x is e to the x. Antiderivative of negative 2 is negative 2x. Thank you for participating. And then what do I have to have? Plus c. So everything the same so far. Here's the difference. We are not looking for the general solution. This is the general solution. Why? Because it's plus c, plus some constant. We don't know what that constant is. What we are doing now is finding out what that constant is. We're looking not for a version of the equation that gives us out. We are looking for the particular equation that will pass through that point. So what do? We plug in 0 for x and 5 for y and figure out what the hell c is. That's it. So 5 for y, so I get 5 equals e to the 0 minus 2 times 0 plus c. Plug in 0 for x and 5 for y. What is e to the 0? 1. And then negative 2 times 0, that's gone. This becomes 1. So c is what? C is 4. So we go back and plug that into our original answer that we came up with. And our particular solution is y equals e to the x minus 2x plus 4. That is our particular solution. This is the solution to our problem. Okay, one that goes through a particular value we want. It's a particular equation that fits our situation completely. Your turn. Okay. So I have dy dx equals 2x cubed minus 5x plus 3. So dy equals 2x cubed minus 5x plus 3 dx. Integrate both sides. Y equals, let's see, that would be 1/2 x to the 4th minus 5/2 x squared, right? Plus 3x plus c. Okay. And then plug in -1 for y and 3 for x and go to town. So -1 equals 1/2 times 3 to the 4th minus 5/2 3 squared plus 3 times 3 plus c. So this is 9, and I'm going to go ahead and subtract 9, so I get -10 equals 81 halves minus 45 halves plus c. So -10. 81 minus 45 is 41 minus 5 is 36 halves plus c. And 36 halves is 18, right? So I get 18, subtract 18, -28 is c. Yeah, the arithmetic's kind of a pain on this one. So my final answer, y equals 1/2 x to the 4th minus 5/2 x squared plus 3x minus 28. Okay. Now, so far these have not been terribly difficult antiderivatives to do. Don't worry, that will change. Not for the most part today, however. Now, it is true that you can take the derivative of any function. If you have a function, you can do the derivative. It may be a long, complicated process that you have to be careful about, involving the chain rule and quotient rule. And if you have x's and y's mixed together, it might involve implicit differentiation. But you will eventually be able to come up with dy dx equals some function. No matter what, you will be able to do the derivative. Sometimes it's a real pain in the butt, but you can do it. There are rules that let you do that. Antiderivatives, on the other hand, sometimes they are essentially impossible to find. Sometimes they are actually impossible to calculate. How do we solve differential equations if we cannot find the antiderivative? We use slope fields. Okay. Differential equations can also be using slope fields. Each dash represents the value of the differential equation at that coordinate as a slope. A particular solution can be found by tracing the graph of the slope field passing through the initial value. So we are going to work with these in more detail next time, but I did want to bring them up here. Okay. So these are two slope fields. The first one is dy dx is equal to x minus y. Second one is dy dx equals y. Those are actually doable. Well, second one's doable by hand, taking antiderivative. First one, not really so much. I'm not sure I could. That'd be a tough one, really tough one to do. x minus y. There are rules for doing that. We will learn actually how to do this one in a couple of weeks. Okay, but in the meantime, you also do have to understand kind of what's going on with differential equations. So my differential equation for this first example, dy dx equals x minus y, and don't try to copy the slope field down. We will be doing slope fields, and we'll talk about how to make them, and you will have to make a few, but I'm not going to make you do this. Okay, I will either give it to you or tell you how to do it on a computer or your calculator. Many calculators are not able to do slope fields. I know some of the high-end TIs are, so the high-end Hewlett-Packards are. I'm not sure other than that. I know some calculators, some computer programs will do it, some won't. Desmos will not do this. Graphmatica will. I actually downloaded Graphmatica on my computer here so I could do a couple if I needed to. And I do have Graphmatica on my iPad. It will work on Apple products and PCs. It will not work on Android. They have not yet gotten it to work for Android. So here's what you're doing. So if I have a coordinate, let's say here's the point, here's the point 1, 2 right here. So what I do is I plug in 1 and I plug in 1 for x and 2 for y. 1 minus 2 is negative 1. So, oh, sorry, that's the point 1, 1. So right here. So what do I have? I have a slope of negative 1. So I have a little dash that has a slope of negative 1 at that coordinate. That's what a slope field is. Each one of those little slashes is the value of the differential equation represented as a line with that particular slope. So all the horizontal ones all have our lines with a slope of 0. Where is x minus y equal to 0? Where x and y are equal. So all the points 1, 1, 2, 2, 3, 3, 4, 4, negative 1, negative 1. That's why on that diagonal line where x and y are equal to each other, every single one of those has a little horizontal dash. Because the value of x minus y at every one of those coordinates is 0, which means I have a little horizontal line because it has a horizontal lines have a slope of 0. Okay, does that make sense? And when you're talking about a particular solution, what you do is you pick a coordinate that you want to go through. Let's say I want to have the particular solution that passes through the point 2, 0. So I want to go through that point here. Well, what I do is I trace from that point following the slope field. So when I go up, it kind of goes like this, and then goes like kind of asymptotic. And then as I go down, it kind of goes down like that. That's the particular solution that passes through that point. Doing it by hand, that's all you can do. Your calculators and computers will do it a little more exact, but they do essentially the same thing. They just have a very complicated algorithm that computes it for you. Okay. If I want to do this one here, I want to find the particular solution that goes through the point 0, 2. I start there, and I follow my graph. And if I start down here, same thing. Follow what my graph tells me to do. What does the slope field tell me to do? Oh, it gets a little steeper, so I get a little steeper. I go a little shallow, this thing is shallow. Yes.
Are there any like things like that where instead of it showing a line, it gives you like the actual value of the slope?
No, no, these are all just little dashes. That's how slope field works. Yeah, and it's like I said, we'll work on them next time, but this is a good time to introduce it because, like I said, what if you can't solve the differential equation? What is the antiderivative? You can't find it. There is still a way to represent a solution. There's still a way to represent it. May not be something you can work with as easily as an equation, but it does work. Okay? Any questions about that? Oops.